We are recording.
All right, so chapter 31, monads, monoids, and categories, as if we haven't seen enough of those already.
Sure.
There's no good place to end a book on category theory. There's always more to learn. It is a very vast subject, and at the same time, it's obvious that the same themes, concepts, and patterns keep showing up over and over again. Yeah, these three, they show up all over the place, like repeatedly.
Pretty
We've seen that,
much.
right?
Pretty much.
There's a saying that all concepts are Kan extensions, and indeed, you can use Kan extensions to derive limits, colimits, adjunctions, monads, the Yoneda lemma, and much more. The notion of a category itself arises at all levels of abstraction, and so does the concept of a monoid and a monad. Which one is the most basic? As it turns out, they are all interrelated, one leading to another in a never-ending cycle of abstractions. I decided that showing these interconnections might be a good way to end this book. So yeah, I like this chapter a lot. So let's just dive into it. So first of all, by categories.
They are not hello categories, they are by categories.
Yes, they are by categories.
Okay.
One of the most difficult aspects of category theory is the constant switching of perspectives. Take the category of sets, for instance. We are used to defining sets in terms of elements. Empty set has no elements, singleton has one. A Cartesian product is a set of pairs and so on. But when talking about the category sets, we had to forget about the contents and concentrate on the arrows between them, right?
Yes.
Sometimes we looked under the cover, um, but those are just sanity checks, basically.
Yes.
A functor is defined as a mapping of categories. It's natural to consider a mapping as a morphism in a category. A functor turned out to be a morphism in a category of categories, small categories if we want to avoid questions about size. And by treating it as an arrow, we forfeit the information about its action on the internals of a category, its objects and morphisms, just like we forfeit the information about the action of a function on elements of a set when we treat it as an arrow.
Yes.
But functors between any two categories also form a category.
No, that's
And
also
this,
nothing new.
yeah, that's nothing new. Then we are asked to consider something that was an arrow in one category to be an object in another. Um, in the functor category, functors and objects, natural transformations are morphisms, and the same thing can be an arrow in one category and an object in another.
Yes, perfect. So good so far.
Instead of switching between the two views, we can try to merge them into one, and that's how we get the concept of a two category, which we've seen a while back, right?
Yes.
Where we have objects which are called zero cells, morphisms are one cells, and morphisms between morphisms are two cells, and here's the picture.
Um, yeah, so it's basically like an inception process, right? So you have two balls and you have an arrow between the balls. Then if you have an arrow between the two arrows, that's the second degree.
Yes, basically.
Yeah.
The
And
category
by
of
the way, you can have this process indefinitely, right? Like imagine the two parallel arrows from two available morphisms between morphisms. You can have morphisms between morphisms between morphisms.
yeah, you can have a you can probably
Incels. It's almost incels. It's almost the political controversial term.
uh, the problem of trying to make a category of natural transformations is that I think it might be doable, but you have the complication of okay, you have to care about the start and end points
Many
of the
layers
start
below.
and end point. Yeah, layering starts to become
Yeah,
difficult, I
layering.
guess.
Yeah, the indexes, like the when we use the indexes like the natural transformation at n, you're gonna have alpha at n, at m, at k, at t, like it goes all the
Yeah,
way down.
yeah. So the categories of categories cat is an immediate example. Yeah, that's basically this. The lot of a two category tell us that one cells between any two zero cells form a category. In other words, CAB is a home category rather than a home set. And this fits nicely with our assertion that functors between categories form a functor category.
Wait, can you go back to the previous sentence? The laws of a true category tells us that one cells, which are functors, between any two zero cells form a category. And the zero cells are
Objects. They are the objects, A and
objects.
B.
In other words, CAB in a home category is a home category rather than a home set.
Yes.
But oh, it's because A and B's are categories.
No, it's because well, it's because if you take all the morphisms from A to B, in this particular context, those morphisms are actually functors,
Because the
which
objects are
means that
categories.
and the objects are categories.
Oh,
Yes.
so okay, so that's why it's a home category. Okay.
Um, in particular, one cells from any zero cell back to itself also form a category, the home category C from A to A, but that category has even more structure. Members of that can be viewed as arrows in C or as objects in C from A to A.
Yes.
As arrows, they can be composed with each other, but when we look at them as objects, the composition becomes a mapping from a pair of objects to an object. It looks very much like a product, a tensor product to be precise, and this tensor product has a unit, the identity one cell. It turns out that in any two category, a home category C from A to A is automatically a monoidal category, with the tensor products defined as composition of one cells.
Wait,
Associate.
that's a lot of words.
Okay.
So members of CAA can be viewed as arrows in C, which is true because they are morphisms in C, but they are objects in CAA because these morphisms will be the objects of CAA. So if you compose those arrows and you look them as objects, so in the if they are objects, the composition becomes a mapping from one pair of objects to one. So basically, like a pair to a, it's a binary
To a
function.
simple. Yes, yes.
In it turns out that in any two category, a home category CAA is automatically a monoidal category with the tensor product defined as composition of one cells. Well, that makes sense because the one cells are basically treating the morphisms, right? So they can be
Yes.
composed.
Yeah. Basically, concatenative programming, essentially.
I don't follow that jump, but
Uh, because you are treating basically you're treating composition of morphisms as a monoidal product, um, which in the context of concatenative programming, you think of it as a program concatenation, essentially.
wait. So in the case of fourth or something, you're basically saying that two functions in a row, their composition is actually a monoidal. It's basically interpreting the stack as a monoid.
Not the stack, the program code, actually.
That doesn't make sense to me because the functions that you're writing is actually manipulating the stack, not the code.
Yes, but when you want to compose two functions, you just write one after the other.
Yeah, I don't see how from that we go. I'm not seeing the connection. I'm sorry.
Uh, well, in fourth, this is a little less obvious. You would have to think about something like factor or joy, where programs are literally lists of operations.
Yeah, but let's imagine that you have a programming language, an arbitrary programming language, an imaginary actually programming language that you have functions in sequence like add and then multiply and then in sequence, like written in sequence. How would you
Yeah.
interpret these sequence of operations with this interpretation here?
Uh, well, if you have two such sequences, you can compose them together by just putting one after the other. Like, you know how you would do basically. Well, basically, a program is a sequence of primitive operations,
Yes.
and if you want to compose two programs, you just concatenate them.
Yes, I don't see how that's related to the monoidal category.
That structure is monoidal because it's associative and there is an identity element, which is the function that just returns.
I don't
Which you
think, but in well, at least to my knowledge, it's not associative at all. The order matters.
no, it is composition is associative.
No, composition is. Composition is.
Like, okay,
Ah, wait, I think I see. I think I see what you're saying.
if you have a function A and a function B, and you define that as let's call it f. Okay, f is A followed by B. A composed with B. You call A and then you call B with the result.
Yes.
And you have a C function. Then let's also define G as B followed by C. Okay.
Yes.
Basically, the program fragment F and C is equivalent to G after A. Because if you
Um,
expand these, F is basically A and B and G is basically B and C.
that is correct.
This is associative. This is literally associativity of function composition.
Okay, so your argument is that when you're writing a concatenative programming language, you're actually writing a bunch of monoidal operations.
Well, writing the programs itself is a monoidal operation.
Yes, no. Well, a program being defined as a sequence of primitives in a concatenative programming language, then the program is a sequence of concatenative programming primitives, which means that the entire program is just a bunch of monoid operations. But what is the monoid? That's what I'm trying to to try to identify. You
Okay, you
said it's
have,
not the stack,
it's
so
not the stack, it's the program code itself is the monoid.
the program code itself.
Yes, because you have the identity function, which is just the empty program. Um, if you concatenate the empty program with anything else, you just get that other thing, right?
The order
Like it
doesn't
doesn't
matter.
matter. Yeah, doesn't matter if you say F means I wanna do nothing, then I wanna call A, then I wanna do nothing again. Like this doesn't matter. This doesn't matter at all because that's literally the identity function.
Okay,
And
so
then
your argument is that the program, a program written in a concatenative programming language is itself a monoid.
yes,
Okay, okay, okay. Let me. I see the vision. I see the vision.
yeah, and here we're saying okay, one cells can be viewed as objects, but also as arrows depending on which category you're talking about. But when you look at them as objects, composition becomes a monoidal tensor construction, essentially.
Which I
And
already
so you have,
forgot. What the heck is a tensor product again?
it's a generalization of a product. It's basically a data constructor of two variables together with a type that you can fill in that basically means no information. So it can have the either type together with void. That's a possible tensor product. In this case, the tensor product is actually the product, and the unit is unit.
Okay. Okay, let's continue.
All right, so let's see what this means in our canonical example of a two-category cat. We have this home category of endofunctors on A, so cats from A to A. Endofunctor composition plays the role of a tensor product, so the identity functor is the unit. Um, We've seen before that endofunctors form a monoidal category, and we used this to define monads earlier. But now we see that this is more general. Endo one cells in any two category form a monoidal category. And we'll see that later.
Wait, can you scroll up a little bit? Oh man, I can't blink in these chapters because otherwise I'm gonna get lost. So, functor composition plays a role of a tensor product. Yes, the identity functor is a unit. Yes, we've seen before endofunctors form a monoidal. Yes. Okay, no, let's continue.
In a general monoidal category, we did not insist on the monoid law being satisfied on the nodes. It was often enough for the units and associativity laws to be satisfied up to isomorphism.
Mm-hmm.
In a two category, monoidal laws follow from composition laws for one cells, and those laws are strict, so we always get a strict monoidal category. But it's possible to relax those laws as well, and we can say that the composition of the identity with another one cell, f from A to B, is isomorphic rather than equal to f. And isomorphism of one cell is defined using two cells.
Wait,
In other words,
wait, man. I
okay,
need to be careful because now we have layers. So we have levels, and then the interpretation changes because of the level view perspective. So in a two
okay,
category, monoidal laws in CAA follow from composition laws from one cells. Okay. These laws are strict, so you always get a strict monoidal category. In this, however, possible to relax. That a composition of the identity one cell, so that's the identity interpreting them as arrows,
yeah, this would be the identity functor in cat, for instance.
with another one cell, which is also an arrow, is isomorphic rather than equal to f. Why? Oh, we're doing this to be more relaxed.
Yes,
Isomorphism for one cell is defined using two cells. In other words, there is a two cell.
rho
Oh,
because
yeah,
Greek
because in
letters.
this case the composition is an object because this is a two cell layer.
Yes,
Okay, okay, and that has an inverse.
yes, and here's the diagram.
So if you go from A to A via identity and then you use F, you go to B, but you can compose. Well, you can go from the composition F after ID to F using rho.
Yes.
Okay.
Yeah, and this rho is an isomorphism, so you can go backwards as well.
Yes.
We can do the same thing for the left identity and associativity loss, which would be with ID on the other side, right?
Yeah, I have a question though. Why do we have the need to make these relaxed? Why can't we just talk about strict?
Because this is actually more general.
Okay.
Like you have fewer requirements, so it can fit more things, basically.
Yeah, okay. No, that's okay.
This kind of relaxed two category is called a bi-category. And there are some additional coherency laws, which we saw them before, right? When we were talking about, what was it? Topos, I think, where we were very concerned about monoidal categories. No, it was about enriched categories, actually. Right.
I don't remember. In rich categories, what is that chapter? Which one?
The one where we try to get away from home sets, so we enrich a category over a monoidal category. And I mentioned that because of the coherency laws, because they didn't require, back then, we didn't require the monoidal category to be strict, but that implied that we needed some coherency laws about dealing with like multiple levels of applying the associative isomorphisms, basically.
Yeah, I don't have that much of a recollection. I'm just looking at this chapter. It's saying that a category is enriched when you replace the home set with a home object.
Yeah, if you scroll down a little bit, there
Oh,
should be a bunch
it's
of,
basically abstracting out all the home sets to a single object.
yeah, to a home object, which can be arbitrary, not necessarily a set.
Okay, no, let's continue.
Uh, as expected, endo-1 cells in a bicategory form a general monoidal category with non-strict
Yeah,
loss,
that's just
which,
what we just established that. So
yeah, we just established that. An interesting example of a bicategory is the category of spans. A span between two objects A and B is an object X and a pair of morphisms, like this.
so a span between two objects is when you have a common element paired with morphisms to go from the common element to each one.
Yes.
That's a weird name, but okay.
You might recall that we used spans in the definition of a categorical product. We want to look at spans as one cells in a bicategory. The first step is to define a composition of spans. So suppose we have an adjoining span using f prime and g prime and y
Mhm,
and b and
mhm,
c,
mhm.
and it and going left with f prime, you go to the same b that you get from x and g. All
Yes,
right.
yes. So far, so good.
The composition would be a third span together with an apex z. The most natural choice is the pullback of G along F prime. So remember that the pullback is an object Z together with these two morphisms with this condition, which is universal among all such objects. So we get a diagram that looks kind of
G
like this.
after H. Yeah, this is basically like similar to the natural condition, naturality.
Yes.
Yeah, no, this makes perfect sense.
For now, let's concentrate on spans over the category of sets. In that case, the pullback is just a set of pairs from the Cartesian product x and y such that um, g of p, which is the left element of the pair, is equal to f prime of q, which is the right element. So basically, p and q in this case would be like x and y from the diagram up there.
Yes.
A morphism between two spans that share the same endpoints is defined as a morphism age between their apices, such that the appropriate triangles commute. So um, So we have this morphism between the x and y, right?
Yes.
And then you have the components going from A and B, and this all has to commute to define the notion of this would be a two cell, right? Basically,
Wait,
which is
though.
equivalent.
Would you
Okay.
say that the morphism between X and A is G, and the one between X and B is what is the other one? F prime? Is
Yeah,
that what you're saying? What we are saying here? Maybe I'm wrong. That's why I'm asking.
yeah, that's basically it.
Hmm.
So to
Okay.
summarize, in the bicategory span, you have zero cells, which are sets. The one cells are the spans themselves, and the two cells are span morphisms, so DH here, basically.
Wait, no, let's
Uh,
go back to what I just asked because I think I said bullshit. So where is the G and the F prime in the below diagram?
where's the G and the F prime? Well, the G would be this arrow from X to A, and the F prime is this other arrow from X to B.
But P and Q are X then. No. What are P and Q in that then?
Uh, oh, this is about defining the.
The
This is actually
pullback.
about defining the Z here, not about defining the morphisms
Oh,
between.
okay, okay. So they don't have the name that we should not use the same names then. Okay, I got it.
Right, a morphism between spans that share the same endpoints. So in this case, X and Y, they both go to A and B. It's a morphism between the apses, yeah, and the triangles has to commute. So
No, that makes sense.
we've seen another example of a bicategory before, the bicategory prof of profunctors, where zero cells are categories, one cells are profunctors, and two cells are natural transformations. And the composition of profunctors was given by a coend.
Yeah, but you jumped a sentence. An identity one cell is a degenerate span in which all three objects are the same and two morphisms are identities.
Yeah, so in this case it would be like you have this object, and then you have an arrow pointing to itself and another arrow pointing to itself as these two, right? Instead of pointing to A, A would be equal to
Yeah,
Y.
but that would be a span from Y to Y, I guess.
Uh, well, it would be the identity span basically.
Yes. Okay. Okay. This is just an example on how like the layers stack on top of each other because we're basically naming like there is level 0, level 1 and level 2. They have separate members in each level.
Yes, and they all interact in particular ways that we are seeing.
Yeah.
Now
That's
we go to monads. You should be pretty familiar with the definition of a monad
Wait,
as a
wait.
monoid.
I think
Okay,
your screen froze because I'm still looking at the span. Oh, now it's back. Now it's back. Okay, let's go.
all right. So monads, you should be familiar with the definition of a monad as a monoid in the category of endofunctors, that famous meme, right?
Yeah.
Let's revisit this definition with the new understanding that the category of endofunctors is just one small home category of endo-1 cells in the bicategory cat. That's pretty
Wait,
dense,
by
but
category is the one with two levels but non-strict, right?
yes,
Okay.
exactly.
Okay.
We know it's a monoidal category because the tensor product comes from the composition of endofunctors, and a monoid is defined as an object in a monoidal category, where here it will be an endofunctor T, together with the two morphisms.
Morphisms
Together with two,
between endofunctors are natural transformations, yes.
they are natural transformations. One morphism maps the monoidal unit to T, and the monoidal unit is the identity endofunctor. And the second one is mapping the tensor products of
Yeah, this is
T
join.
and T. Yeah, this is join basically. So
There it
here's
is.
the mu and here's the diagram. Uh, yeah, these are return and join in Haskell. And we know that monoid laws become the monad laws. Now let's remove all mention of endofunctors from this definition. We start with a bicategory C and we pick a zero cell A in it. Okay, so A is an object.
Mm-hmm.
Um, we've seen earlier the home category in C from A to A is a monoidal category. So we can define a monoid by picking a one cell T and a pair of two cells, which are these two. And if they satisfy the monoid laws, which, well, they do
Wait,
because,
I got lost on the layers again. So level 0 is an object in a bicategory,
yeah, level 0 is
which,
an object.
yes. And then we are saying that the one cell is T, and T is the functor.
Yes.
And so we are going, so N and mu and me are natural transformations.
Yes, they are. They are two cells, which are natural transformations in this case.
Uh, the object level 0 is a monoid.
Uh, level 0. Um, well, not necessarily actually, but the home category of C from A to A is a monoidal category.
Yeah, but I'm trying to identify, like I know I shouldn't do that, but I feel that in this example we could identify what are the objects of this example.
Well, the object at level 0 is whatever. You
Oh,
just pick
okay, it's
whatever
whatever.
because you need the identity. Well, you need the home category of the A to A basically for whatever A you choose, right?
Mm-hmm.
We know that this home category is monoidal because this is a bicategory, right?
Mm-hmm.
So we can define this monoid in this home category by picking a one cell, which we call T. That's a functor basically, and a pair of two cells, which are natural transformations, and they must have this signature.
Yeah.
And this is what we call a monad.
Yes. Yes. So here's the drawing. We have
Yeah, here's the
A,
drawing.
we have identity, then we have
We have T, which
T.
is the, yeah. And then we have eta that goes from the identity to T. And we have mu that goes from the product T and T back to T.
Yes. Yes.
Uh, yeah. That's a much more general definition of a monad using only 0 cells, 1 cells, and 2 cells. It reduces to the usual monad when applied to the bicategory cat. But let's see what happens in other bicategories. Let's construct a monad in span, which is the bicategory we just built up here
Mm-hmm.
with this thing.
Mm-hmm.
All right, so we pick a 0 cell, which is a set that, for reasons that will become clear soon, I will call OB, okay?
Yes.
Next, we pick an endo 1 cell, a span from OB back to OB.
Yes.
It has a set at the apex, which I will call R, equipped with two functions, the DOM and the COD.
Okay.
Let's call the elements of the set R arrows. And if I also tell you to call the elements of objects, you might get a hint where this is leading to.
Wait. Wait. Let's call the element. Okay, so we have sets here, right? So,
Yeah,
uh,
R is a set and ob is also a set.
okay, so we have arrows as objects of the set R, and we can go to another set, OB, in two different ways, from using DOM and COD, and
Yes,
the elements of OB are called objects.
yes,
And we are mapping elements from R, which are arrows. We are mapping arrows to objects.
yes.
I don't know what this is leading to, but let's continue.
The two functions DOM and COD assign the domain and the codomain to an arrow. Now, to
Wait,
make our
wait. That means that we are deconstructing a function?
we are deconstructing a function. No, this is an arrow.
Yeah,
The domain of an arrow is an object,
and yeah.
and the codomain of an arrow is another object.
Yeah, we are literally splitting what is a function in three different sets and two different functions.
Basically.
Okay. That's weird, but okay.
Now, to make our span into a monad, we need two cells, eta and mu. The monoidal unit in this case is the trivial span from ob to ob with the apex at ob and two identity functions, which is the identity span as we established earlier, right?
Mm-hmm.
The two cell eta is a function between the apices ob and r. In other words, it assigns an arrow to every object. Okay?
Wait. The choose cell and n is a function between the two apices OB and R. N assigns an arrow to every object. A choose cell in span must satisfy commutation conditions. So you're saying that DOM after eta is equal to identity and COD after eta equals to identity as well.
Yes.
Um, um, Wait, let me see eta again. Eta is the
Eta,
one that goes from identity to T.
yes.
Um, okay, back to the other one. Eta is the one goes from identity to T. Uh, I don't know if I follow. Why eta is going from OB to R here?
Because the identity span is a span that has an apex and the two sides being equal, and the two morphisms are identity. So this is actually the identity arrow, you could say.
No, yes, that's true, but eta is going from OB to ARR. Why?
Yes.
We should go from
Uh,
identity to T, right?
in this case, T is R.
Wait, but T is a functor. Am I wrong? I just asked this before.
Uh, T is a functor. Yes, it is.
So how R is well, R is a set which is a functor, so that's correct. Am I saying bullshit?
Well, it is a set, but the reason it's a functor is because this R is the apex of a span. That's why this is a functor, because spans are one cells. They are functors in this category, in this bicategory.
Okay, repeat, please.
Okay, this R together with this domain and the codomain going to object, right?
Mm-hmm.
These three things together, they are a functor of this bicategory. They are one cell.
They are a
Okay?
functor of this bicategory,
Yes. And this ob with the two identities in the two obs are another functor
which is the
in the
identity
same.
functor.
Yes. And the eta is a natural transformation going from one to the other.
Um, Actually, that I think that makes sense because it's saying that T, which is R in this case, is an endofunctor, right? Which is
Yes.
true because they are all spans.
Yes.
Okay.
In components, this becomes this, which is the same as this diagram, right?
Oh, wait, so if you pick OB, you apply N and then DOM. Yeah, this is the same as the diagram.
So ob is an object in ob. In other words, eta assigns to every object an arrow whose domain and codomain are that object. Um, I think this D is not supposed to be here. We'll call this special arrow the identity arrow. Okay, eta is the identity. Well, actually, to every object an arrow whose domain and codomain. Yeah, this is the identity arrow. Actually, this is the. See, it goes from objects to itself, basically.
Well, it must be because otherwise the identities on the outside would not match.
Yes.
Okay, so this is okay. So this is a very convoluted way of saying identity.
You know, I just thought of this. Maybe category theory is just an exercise in seeing how convoluted you can be and still be talking about identity.
Oh, I don't know about that. That's a little bit too much, but this particular diagram, yes.
Uh, anyways, the second two cell mu, which is yeah, there's a diagram down here, acts on the composition of the span R with itself. The composition is defined as a pullback, so its elements are pairs of elements from R, pairs of arrows, and the pullback condition is this. The codomain of A1 needs to be equal to the domain of A2.
Wait, let's go. Let's backtrack. I need to read that again. The second shoe cell mu acts on the composition of the span AR with itself because this is R composed with R needs to go to R.
Yes, this needs to be able to join, essentially.
Yes. So its elements are pairs of elements. The pullback condition is that the codomain of one is the domain of the other.
Yes.
Wait. No, that must be the case though,
Yes.
because you are grabbing arrows.
Yes. We say that A1 and A2 are composable because the domain of one is the codomain of the other. And here's the diagram.
Okay, so if you make a product out of the R, which is T, you can apply mu to. No, no, no. That I think that makes sense. That this makes sense because what we're essentially saying here is that you can grab two arrows, and if this condition above applies, you can actually combine it into a single R.
Yes.
Okay. Okay, that actually follows.
The two-cell mu is a function that maps a pair of composable arrows to a single arrow A3 from R. In other words, it defines composition of arrows, which is, well, it makes sense, right?
Makes sense.
It's easy to check that monad loss corresponds to identity and associativity loss for arrows. We have just defined a category.
So all told, the category is just a monad in the bicategory of spans. Yeah, that's what I just thought. Why don't we start the conversation with that? Like, I think this idea, not necessarily the idea of bicategories, because that's a little bit too much, but I don't recall at all mentioning spans in the chapter one.
Well, we didn't mention bicategories in chapter 1 either.
But you don't need bicategories to do what I'm saying. You just need to present spans in the beginning, because spans puts it in such a way that already makes give you the to give you the reader the ability to interpret functions as objects already, because we're kind of reaching this conclusion right now at the end with the 0, 1, and 2 self stuff. But in if chapter 1 we start talking about spans, I think it would be we would have an easier time right now, although this is not hard.
Well, yeah, but yeah, it's kind of crazy that you can define a category as a monad.
Yeah, actually.
What is amazing about this result is that it puts categories on the same footing as other algebraic structures like monads and monoids. There is nothing special about being a category. It's just two sets and four functions. In fact, we don't even need a separate set for objects because objects can be identified with identity arrows. They are in one-to-one correspondence. So it's really just a set and a few functions. And this is the end of the book. Considering the pivotal role that category theory plays in all of mathematics, this is a very humbling realization.
Okay, so we're basically saying that if you have some functions and you have a set, that's what a category is. Yeah, but that's not really that surprising, I would say, in the sense that because we already established this before. If you are associative and you have composition and you have and the composition is associative as well, like that, it's not that hard to be a category. But the fact that you can put a category on the same level of abstraction as a monad is a little, it's surprising, I would say.
Yeah, I like this chapter. And it's
uh,
not even that long actually, if you think about it.
well, after a very gigantic journey of 31 chapters and many, many hours of discussion and considerations, yes, it's not that long. Um, okay, final considerations then. So this is the last chapter. We have 17 minutes to make any comments.
I really like this diagram. I think it's very nice.
Okay, my comments about the book are the following. I would say that the book did a good job in the beginning, grounding itself in programming, in the sense that you could feel it was very palpable, the mapping between the theory and the programming. And I
Yeah.
felt that as we went forward, that mapping get started to get extinct. Even though there were mentions of some ideas that you can use for a parser or a compiler, we never seen code with that. And there are
That
some.
is
Go on.
yeah, that is true actually. Like I think after chapter what is it? Chapter the lemma, free and forgetful, monads. Yeah, I think about after chapter like 25, I would
I would
say.
put 24. No, actually, no. At 24, there's an interpreter, so let's put 25.
Yeah, chapter 25 and onwards, there's not really much programming. This is more stepping into the realm of like actual pure mathematics.
Yeah, which I think it's a downside because the book promises to deliver you those concepts from a programming perspective. It may be the case that it's kind of very hard to put that amount of code, and it would be kind of boring for the reader if he put it like, I don't know, 300 lines of Haskell just to demonstrate something. But I think that's what you're buying when you're deciding to read something like this. You are buying the chance of getting bored with a bunch of code that you're going to have to read yourself. And I think that would be fine because the problem with this type of stuff is that if you don't have uh, the mapping being done by the author and the reader needs to go after that, the reader needs to be so comfortable with the theory that it's going to take a long time for him to identify, uh, no, this concept actually could be applied to implement this other thing. We are not smart enough to make that jump. The author is. So mentioning to us is something is better than nothing, but having the code would be great because then we could actually see the patterns that we're going to see on our daily jobs and say, hey, maybe I should actually rewrite all of this stuff with this other mentality in mind, and I'm going to have an easier time finding the correct solution.
Yeah, that's something that would be very helpful, but as you mentioned, this is kind of lacking in this like last what, 6 chapters?
Yeah, 6 chapters. I also think the risk of confusion meme should not be true.
Yeah, it's kind of sad that it actually is. I wish it wasn't.
Um, okay, but about recommendations, like if we would recommend, right? I think that if your expectations are that you're gonna read this and you're gonna immediately see like a jump in productivity in your whatever job you're doing in programming, I think you should not read it. I don't think there's enough programming being grounded programming here that you're gonna actually be able to immediately see a gain. So if that's your expectation, you should not read it. If you are willing to read it with an open mind for the ideas and the essence of it, and if you have a gain in the future in programming, that's cool. But you're not really asking for it. I think it's a valid reading. I think.
Yeah, this is good if you want to know the concepts. But whether or not this will make you more efficient as a programmer, that's kind of doubtful.
And I would also say that the efficiency graph has another variable, which is how comfortable you are with those things. So as I said multiple times, I'm not comfortable with limits and co-limits and ends and co-ends. You may say that the jump in my programming didn't happen because I didn't have mastery on those ideas yet. And as soon as I get the mastery, I will notice a jump. That may be true, right? You can only judge something properly if you actually know the thing properly.
Yeah, but at this point, we don't really know enough to say if that's the case or not.
Yeah. And I would also recommend reading with somebody else because I think reading this by yourself would be like a chore.
Unless you're a mathematician, but then why are you reading a book for programmers?
Well, because you want to be multifaceted, like you want to know how to do the two things. Uh, yeah. I think that's it. That's all I have to say. I wanted more examples in the code. I think the risk of I mentioned the risk of confusion and the usefulness, right? Because a lot of people put all of this controversy about you don't need category theory to do Haskell, and that's true. You can do very useful stuff without knowing that. But how can you argue that there isn't very useful stuff that you're going to have an easier time achieving by knowing it? The category theory behind it. I don't think you can make that argument out as without knowing the category theory. You need to like it's insane. I don't know. I don't know how
Yeah,
people
it's
go to these conclusions. Like, oh, you don't need for anything. How can you say that? Um
I
do
think
you?
it would be better to say that you do need it, but you don't need to understand everything all at once. You can pick it up gradually as you require.
Yeah, and I think there's also some sort of misconception that everyone that is reading is smart, and if you're not understanding, it's the book's problem, not yours. Like,
Yeah, that's. I don't think that's a good way of going about any book, to be honest.
yeah, that's basically arrogance. That's the lack of humility. You are basically saying that because you're not understanding it, there must be something crazy about the people writing it and not about the people reading it. And as someone that is very dumb myself, I can assure you that there were a lot of things that I didn't get it the first or second time I read it because I was not smart enough. So to me, it's just an excuse, it's just a coping mechanism to say, do not accept the reality that maybe, just maybe, you are dumber than you thought.
Well, there's a solution to that. You can just keep trying. Try to look at the problem from the thing that you don't understand from a different perspective, and maybe you will understand it.
No, 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 but
Like,
that's the thing, Mario. If people do what you said, like, oh, I don't understand how CT is solving this problem. I'm going to try to change the CT and solve the problem because then I'm going to have ammunition to say that CT is useless.
no, no, no. It's more like try to look at it. How can I say this? Not for the sake of, okay, I'm going to look at it from a different angle to try to say it's useless, but rather to try to relate to something else that you may be already familiar with. Because, like, at the end of the day, this is mathematics. It has connection to a bunch of stuff, right?
Well, yes, there are connections with a bunch of stuff, but you also may stumble upon the problem of maybe what you already know is doesn't have the analogies will break along the way.
That is possible, yes.
So like you don't have anything in your arsenal to say, hey, this thing is actually similar to this thing that I already know, so it's fine. It may be the case that you don't have anything close, even close to that. And if that's the case, there's no way around it. Either you accept the reality that maybe you're dumber than you thought, and you're gonna try to learn it the best of your ability, or you're gonna deny that they are saying something useful and just try to do something else about the problem. Solve it in another way. Use a different abstraction, a different theory. Um, so, because to me, the way that you can judge if a theory is worth learning or not is if you can see nonsense in it. So in here, I I couldn't see like any nonsense. Maybe the nonsense is there and I just could not identify it myself. That's the possibility. But from the things that I could understand, there is no nonsense. So I I can't. I don't have an excuse to not try to learn it. That's what I mean. Yeah, but that's pretty much it. Do you have anything else?
I'm gonna say this again. This is a great diagram.
This is the most unexpected way of describing an identity function. Like it's insane. Like it's
This
just
one, right?
insane. Yeah, both of them. Oh no, actually the other one is composition, so not necessarily
Yeah,
identity, but
yeah. The other one is composition.
yeah, this one is basically like, oh, do you want the most amount of space to write an identity? This is it.
And there are actually two identities here, right? Because there's the this thing, obj going to identity to itself, which is
Hmm.
one identity. But then eta is kind of an identity as well, right?
Well, eta is identity to T, so I wouldn't say it's identity, but in,
Because it's pure, right? From the well, actually it's called return in if you go to the monad type class.
yes, it's return. Okay, I'm gonna finish the recording now. Any final
Bye,
words?
future people,
Yeah.
and See you in the next book, I guess.
Well, do you want to give the spoiler? Which book is going to be?
Let's make it a surprise. Why not?
Sure then. So see ya.
See ya.